Have you ever wondered how energy can be stored in remote places like Alaska or Antarctica, where batteries won't survive? One promising answer is pumped thermal energy storage, or PTES. A PTES system stores energy as heat that is continuously exchanged between hot and cold fluid reservoirs using many heat exchangers. A heat exchanger is a system used to transfer heat between a cold fluid and a hot fluid, since many heat exchangers are needed in a PTES system. Ensuring high efficiency and cost-effective manufacturing processes is very important. Unfortunately, current manufacturing processes for heat exchangers are severely outdated, making them expensive and inefficient. With the goal of expanding their PTES work, our sponsor, Echogen Power Systems, tasked our team to use additive manufacturing to build a heat exchanger that is more efficient and cost-effective than current industry standards. Additive manufacturing shows a promising potential to tackle this problem by speeding up the manufacturing process and creating complex geometries to improve efficiency. The cold and hot fluids in heat exchangers are usually separated by a solid wall to prevent mixing of both fluids. Therefore, heat exchanger efficiency increases by maximizing the surface area the fluids are exposed to. Triply periodic minimal surfaces, or TPMS, are structures that offer a high surface area while also minimizing material usage. The complex geometries of TPMS structures lend themselves to additive manufacturing processes. To research the feasibility of an additively manufactured metal TPMS heat exchanger, our team worked to analyze the following key metrics: cost, heat transfer, and pressure drop. While prototyping with metal parts was not possible, a program was created to optimize the geometry of a full-size metal part for heat transfer. Furthermore, through discussions with 3D Systems, a cost and manufacturing plan was created for mass production of metal TPMS heat exchangers. The final key performance metric, pressure drop, is under-researched in current TPMS literature, which motivated our experimental analysis with a plastic prototype. The prototype, printed using a Formlabs Form 4 resin printer, consists of a simple header and core, where the header facilitates the inlet and exit for the single test fluid, water, and the core contains the TPMS gyroid. The prototype also has pressure taps to connect to pressure sensors. A test rig in the multi-scale thermal fluid and energy lab was used to measure the pressure drop in the prototype. As shown here, the test rig was built using a flow loop, water reservoir, pump, voltage sensor, pressure transducer, lab jack, flow velocity sensor, and valves to control the water flow. Through our team's research on pressure drop and geometry optimization, along with expertise from 3D Systems and Echogen's Tim Held, we have created the foundation for an advanced heat exchanger that has the potential to revolutionize heat exchangers and energy storage technologies.